So a pin-jointed truss is used to support a mass of 30 kilograms. The truss has two vertical sides of the design shown below, noting that each bay is a 10 by 10 centimeter square. So a bay is just kind of like a square section here, so each of these represents a bay, and it's marked in for the first one, that 10 by 10, but it's telling us we can use that for each of them, so the horizontal and the vertical sides are both 10 centimeters. So assuming that the mass is supported equally by each side of the truss and that self-weight can be neglected, we need to answer the following questions. So the first one is that we need to construct a free body diagram for one side of the truss. So of course a free body diagram is just a diagram that shows the forces acting on a particular body. So if we scroll down a little bit, I've drawn in the basics of what our body, which is the truss, actually looks like. So onto this we need to add on the forces. So the most obvious force, I think, is this first one here that I'm going to consider, which comes from the weight that's hanging off the truss. So at the moment, this is given as a mass of 30 kilograms, and that's the total applied to both sides of the truss. So if we're just drawing the free body diagram for one side, then each side's going to take half of that, so 15 kilograms. Now we can calculate that as a weight using our equation where weight is equal to mass times gravity. So I'm going to write this as 30 divided by 2, multiplied by the 9.8 meters per second squared for acceleration due to gravity. So this ends up working out as 147, and the units are going to be in newtons. So when I mark it on my diagram, it's acting at this point O on my truss, and we know that it's going to be acting downwards because that's the way that gravity operates. So my first force is 147. Alright, so looking back up here, we're going to get a couple of other forces coming from the supports. So these are the things that are holding our truss up or connecting it to the ground. So let's think about this one first. This is a roller support because it's got the little wheels on it. So we know that roller supports are only going to provide one reaction, and that happens perpendicular to the contacting surface. So we can see the surface here is horizontal, which means that the reaction will be vertical. So I'm going to take a stab as to which direction, as in either upwards or downwards, this is operating in. And it's acting at point R. I'm going to guess it's going up, but we'll see in the calculations whether that was correct. And I'm going to call it RY. So the other support we had here is a pin support. And we know that pins have a horizontal and a vertical reaction that they can provide. So that's over here at point J. I'm going to guess that the horizontal part is going to the right, and I'll guess that the vertical part is going upwards. So I'm calling them JX and JY. That there is pretty much my complete free body diagram, because we're told to neglect our self-weight of our truss. So that means that, yeah, there's nothing else that's really acting upon it. No wind load we're told about or anything else. So that's part A complete. So we'll jump on to part B, which is now to solve for the reactions using our free body diagram. So that means we need to figure out RY, JX, and JY. Now, if we're assuming, which we are going to, that our truss is in equilibrium, so it's not moving, we have three equations that we can use. So sum of forces has to be 0, sum of forces in the x direction has to be 0, sum of forces in the y direction has to be 0, and sum of moments at any point that you pick have to be equal to 0. So we have three equations and we have three unknowns, which means we should be able to solve all of them. So I'm going to start off with by actually selecting the sum of moments equation, and we need to pick a point to consider this about, and I'm going to actually pick point J, which was where the pin joint sat. So the reason is, if I pick that point, what I'm going to see happen is JY and JX are not going to appear in the equation, so I should only end up with one unknown, which is RY, which I can solve directly. If I pick another point, what typically will happen is I will end up with more than one unknown in the equation, and then I'll have to use simultaneous equations and substitution to be able to figure them all out. So I'm going to start with summing moments at the pin joint. And I'm going to consider anti-clockwise as the positive direction. Just as a reminder, a moment is equal to the force multiplied by its perpendicular distance back to the point of interest. So let's say I start with this force here. All right, its size is 147. And I need to multiply that by the distance from its line of action, which is through here where the arrow is pointing, all the way back to our point of interest J. So in this case, my line of action kind of operates straight through this point E, and the perpendicular distance is going to align with the length of the top of the truss here. So I can see that this is going to include like 1, 2, 3, 4, 5 bays, and we were told back up here that each bay was 10 centimeters. So that means there's going to be 50 centimeters in terms of the line of action. I'll mark it in the distance, I should say, from the line of action through here back to our point of interest. I'm going to do it in meters, our base units, so I'll mark it in as the equivalent of 0.5 meters. So down here, to calculate my moment, it's the force multiplied by that distance, and then the last thing I need to think about is the direction that it's going to push around our point of interest. So this force looks like it's going to try and rotate our truss in an anti-clockwise direction about point J, and we're saying anti-clockwise is the positive direction, so it goes positive into the equation. Alright, so let's consider the next force, which is Ry. So that's its size. We need to solve for that in a moment. We now need to multiply it by the distance from its line of action all the way back to the point of interest. So the distance in here is this one we're looking for this time, and we can see that that's 2 bays, which is 20 centimeters or 0.2 in meters, so that we get base units out. So I'm going to pop that in here. And then thinking about the direction, this is going to try and rotate us in the clockwise direction about point J, so it's going to go in as a negative. Oh, and I should have mentioned, all right, we've got 2 other forces on this diagram, but both of them are acting directly through point J. So that means that their distance back to our point of interest is going to be 0. So you could, if you wanted, put in here jy times 0 plus jx times 0, but you can see that they're going to just drop out. All right, so now I should be able to rearrange directly for Ry. So I'm going to leave the 147 and the 0.5 on the left, and I'm going to shift this to the right-hand side, which means that the sign, I should say, is going to switch over. So it goes from negative to positive. And then if I want Ry on its own, what I'm going to need to do is divide by 0.2. So 147 times 0.5 divided by 0.2 is going to give me the answer for this reaction force. And it comes to 367.5, and the units are going to be newtons since we did everything in base. So I'm going to highlight that. And I should mention as well, it's come out positive, which means that we had the direction correct up here on the diagram. So we initially guessed that it was going upwards. So I'll mark that over here. We were correct in that it was going up. So this is 367.5. All right, so we have 2 other forces that we need to figure out, and we have 2 other equations that we can draw upon. So I might go next with sum of forces in the x direction has to be equal to 0. So if we look at our diagram, in fact, the only thing that's happening in the x direction is jx. We don't have any other applied forces or anything going in this direction. So this one's pretty easy. If we substitute in, we're going to get jx must be equal to 0 in order for the forces to be balanced in that direction. So I'll pop in here, that one solved for. And then the last one we're going to get from our last equation, which is sum of forces in the y direction has to be 0. So we do have a few things happening in that direction, so let's substitute them in. So 147 is going downwards, so I'm going to put it in as negative. We've got this 367.5 going upwards, so it's going in as positive. And then I've got jy going upwards, so I'm going to put it in as positive as well. So we need to rearrange this for jy on its own. So I'm going to flick both of these terms to the other side, remembering that that means the signs are going to change over. So if we put 147 minus 367.5 in a calculator, this comes to negative 220.5. So it's come out as a negative value, which tells us that we guessed the direction incorrect. So we guessed that jy was going up initially, but what this is telling us is that it's going to actually be 220.5 newtons going the other way, which is downwards. So that would be our answer for this last reaction force. So I'm going to make sure that it's up here correct on my diagram. So this is our conclusion for it. I'll just try and erase our line here and now draw it downwards onto that joint. It's a bit messy. And yeah, I'll pop it in. So we said it was 220.5. So that there is our 3 reactions, which is the answer we were looking for part B of our question. So part C, which is going to be looking at solving the internal forces in a few different members, I'm going to do in a second video. I'll separate it out. So please look at that for the following part.